Welcome back, and we're going to talk about stability. And by stability, I mean why don't things fall over, or why do other things do fall over when they're not meant to, or at least we hope that they won't, like a book standing vertical. Even the slightest touch can make it fall over, whereas a glass of water is, you'd prefer it not to fall over, but like sometimes it does, but generally it doesn't fall over, at least not on its own. You have to hit it really hard. So why are some things easy to fall and other things harder to fall, right? And let's take a look. Let's say we have a block, and the idea behind this block is it's completely uniform in density, which means that it's not like all the weight is over here somewhere at the bottom and it's all hollow from the top. So it's not like that. It's one uniform solid block, right? And for that, the mass is acting directly on its exact center. So the weight is kind of approximated to work around the center. So the weight is W. And let's say we're trying to flip it over towards the right. Towards the right. So let's say I try to push it kind of like this. I try to turn it like that. Now you appreciate that I'm causing. And let's get a pivot over here. So for this frame of reference, because it's going to turn towards the right and it's going to use this point as, this point won't really move, but it'll try to kind of fall around it. So this is the turning point, so it's acting as a pivot, right? So I'll mark that. And the blue force pushed by me is causing a clockwise movement. And as soon as I lift it, the weight will try to push it down and make it fall counterclockwise, right? So these two are fighting each other. So you can appreciate the heavier the force, the heavier this is, the harder for me to tip it over, and that makes perfect sense. But let me ask you this: at what angle or at what position will it completely tip over? And you've probably played with this. You try to, push something. You try to bend it. Another thing I want to highlight is it's easier to tip something over from the top rather than it is from the bottom, because you generate a larger moment the further you are from the force. Look, if I try to do it at the top, it's easier to tip over. Coming back, now you've probably tried this, that you try to push something like a glass of water, well, not with water in it, but like I'm sure you play with your pencil box or something, and you try to push something and it goes to an angle. Let me bring that over here, kind of like this. You try to push it and the same force is acting on it. Let's find the center. Kind of like that, W. And you've let go, and at that moment you're trying to figure out, you like push it like that, and at that moment you're trying to figure out that will it fall or will it not fall? What's the extreme? How far can you push it? Now as soon as you let go, it all depends on how many moments are acting on it right there and then, right? So over here, what is the moment acting on it? So the moment, not by how much, but is it clockwise or counterclockwise? So if I try to draw a line over here, we still appreciate that the force is not directly on it, but it's slightly towards the left. So the distance is kind of this much, and the weight acting on it is towards the down. So it's kind of like if I try to draw some similar example, the pivot is over here, a very small lever is over here, and the weight W is acting on it. Now, the moment generated over here will be counterclockwise, because it's obvious to see why, right? And this block won't tip over. It'll fall back and be stationary, like standing again, because as soon as you let go, the net moments will dictate where it will go. Now for it to fall over, the weight or the center of mass must cross the pivot and cause a moment on that side. We're saying counterclockwise and clockwise. It's according to our frame of reference, but it doesn't, like, you understand that it's either this way or that way, right? And let's get a third example in, an example where it will actually tip over, hopefully, inshallah. Said no one ever. Okay, here's our pivot again, and I'm eyeballing the weight. It does look like it's on the other side now. The weight is over here, and over here the moment will be, you can see that is going to be clockwise, and once you let go, or even before you let go, this will start falling as soon as the center of mass crosses the pivot line, or this vertical imaginary line where the pivot is, right? Now here's my question: how can I make or design something that's incredibly way more stable than this block over here? Well, the first thing you can do is erase everything on the screen. Let's see if we can get that. Let's see if we can get that close enough. If I want this block to be very stable, what can I do? Well, if this block had a much larger base, it would be much more stable. Let's say if I attach some extended by a bit and attach some triangular wedges to it, kind of like that. And the bigger this is, the harder for me is to tip over. And the weight, the center of mass, because this added mass will change it, but it's more or less, let's assume it doesn't change by too much. And it's a very small piece I attached here. So, and this is now a part of it. And if I try to tip it over, the pivot, it won't be over here, it'll be over here. So by increasing the base, you've moved the pivot, and when you try to move it, when you try to rotate it, this has to go all the way over till here. Now you appreciate now that it'll be much harder to tip over because you've essentially moved the pivot way further, and you'll have to do a lot more work to kind of cross that pivot line. So increasing the base will increase the stability of an object. That's one major way, right? Another way is, if let's erase this. Another way, clean as possible. Okay, another way is if I have the same box and I make sure that the bottom part is much heavier. So it's the same block, but let's say the bottom half is made of lead, which is way heavier, and the top half is all solid still, but aluminum, right? So it looks like as same as this, and the weight hasn't changed. So I've made sure the weight for both of them are the same, but the bottom side is much heavier. So the center of mass for this object is now acting way at the bottom, way at the, why am I using a pencil? Way at the bottom, right? Same weight, but it's way at the bottom. And now you realize that once I try to tip it over again, try to push it from here, this has to cross a lot more distance for me to cross the pivot line, and it'll automatically be more stable. So in a nutshell, either increase the base so it's difficult to cross the line, or have more weight at the bottom of something, so again it's more difficult to cross the imaginary pivot line. So that's how you increase stability of an object and prevent it from tipping over. One more thing I'd like to add is, have you seen those flip the bottle challenges, right? There's always very little water over here, and people who succeed try to do it. Now the trick isn't to, do it with the right angle or anything. The trick only is to do it slow enough when you're flipping that bottle, and because the water is all at the bottom, and that's most because the bottle itself is very light, water's carrying all the weight. You make sure the water, once it touches the bottom, is right at the bottom. So as soon as let's say this is a bottle and it hits the floor, you try to make sure first it hits the base, but it has that inertia, that momentum. It's gonna try to fall, it's about to fall over, but all that water's weight will try to prevent it from moving. So if you have like a little bit of water at the bottom and you try to force it that it falls flat like this, and the water is not bouncing around too much, you do it slow enough, you'll win the bottle challenge, flipping the bottle challenge, because it's much easier to keep it stable like that.